Morning, calculus class today. So just want to get more in depth with the integration techniques. So this one is section 7.4, integration of rational functions by partial fractions. So in this section, you'll be learning how to integrate rational functions by reducing them to sum or simpler fractions. Okay, so we'll take a look at this. So we show how to integrate any rational function, a ratios of polynomial, by expressing it as a sums of the simpler fractions called partial fractions. So let's say that we do have something like this. So let's say that we need to combine that 2 over x minus 1 along with that 1 over x plus 2 together. There's a simple typo here, so this one's supposed to be plus, not equal. So once you combine them, so this one will be written as, well, it's a minus. Supposed to be a minus, not a plus. So it's 2 times the common denominator, which is x minus 1, x plus 2. So the one that's missing here for the common denominator is x plus 2. So we multiply by x plus 2 top and bottom for the first rational expression. And then for the second one, we multiply this one top and the bottom by x minus 1. So we end up with this. And then once you distribute, combine the like term, then we end up with x plus 5 over x squared plus x minus 2. So, and with the integral like this, so we can always separating the terms out. So instead of doing it all together, so we can always using that the separation rational expression. So 2 over x minus 1 minus 1 over x plus 2, integrating it individually. So we do have 2 natural log of absolute value of x minus 1 minus natural log of absolute value of x plus 2 plus constant c. So to see how the method of partial fraction work in general, so let's consider irrational functions p of x over q of x. So where p and q are polynomials. It's possible to express f as a sum of the simpler fractions if the degree of p is less than the degree of q. Okay, so we talk about that in pre-calc. So the polynomial. So let's say that we do have the degree on the top is greater than the degree down the bottom. So that means we're using either the synthetic division or the long division. So synthetic division is that the denominator got to be a linear binomial. But if that's not the case, then we're forced to use the long division process. So once we end up with the long division process, we get the quotient and the remainder over the quotient, over the divisor. Okay, so now let's try one of the example like this. So we try to perform the long divisions, then we end up with things like x squared plus x plus 2 over x minus 1. And then once we end up with the term by term, we can separate the terms out, so we can just integrating it individually. So we do have x to the power of 3 over 3 plus x squared over 2 plus 2x, and then plus 2 times natural log of absolute value of x minus 1 plus constant c. Again, the first 3 terms here, we're just using the basic general power rule. And then for this one, we're using the natural log of absolute value of the quantity. So the next step is to factor the denominator, if that's possible. So this one shows that how to deal with the polynomial, the factorization. So let's say that we do have x to the power of 4 minus 16. So this one can be written as the factor form. X minus 2, x plus 2, x squared plus 4. So the next one, we'll talk about the way to set up the partial fractions. Okay. Okay, so let's just skip all this and then we'll get into the partial fractions. So case 1, the denominator q of x is a product of distinct linear factor. So let's say we do have a distinct linear factor, something like this. So that means once we're separating the terms out, we can put it in as a1, a sub 1 over little a sub 1x plus b sub 1 plus a sub capital A sub 2 over a sub 2 x plus b sub 2, and so on and so forth. Again, this one is for the linear distinct factor. So now let's try one example like this. So we do have x squared plus 2x minus 1 all over 2x to the power of 3 plus 3x squared minus 2x. And you may notice that the degree on the top, it's less than the degree down the bottom. so we don't divide it. So instead, we just want to find out the factor of the denominator. So try to take out the greatest common factor and factor the trinomial. So we do have x times 2x minus 1 times x plus 2. So this one has 3 different linear factors. So one is x, the other one is 2x minus 1, the third one is x plus 2. If we do see any case like that, so the way to factor it out, so we just want to separating the terms out like a over x for the first linear factor, and then the second linear factor we do have b over 2x minus 1, and then the third linear factor would be c over x plus 2. And now we want to find out the value of a, b, and c for those you might be saying that. So multiply by the missing element for the least common denominator, so we end up with this. Okay, so x squared plus 2x plus 1, it's about the comparison with the numerator. So a, so we're missing that 2x minus 1, x plus 2, so that's why we multiply them. So for the second term, so we're missing x plus 2, so we multiply those two terms. And then for the last term, we're missing x and 2x minus 1. And now for the next step here, we want to just regroup them. So once you find out the x squared term, we do have 2a plus b plus 2c. And then for the constant term, for the linear term, we do have 3a plus 2b minus c. So there's supposed to be x right here. That's a little typo. Minus 2a for the constant term. So we want to solve for a, b, and c. So the way to solve for a, b, and c, going back to this one right here, so we can set that 2a plus b plus 2c equals 1. Because it's the matching with the quadratic terms. It's the coefficient of the quadratic term. And then for the linear term here, we do have 3a plus 2b minus c, so that equals 2. And then for the constant term, so it's negative 2a, so that equals 1. So we can solve for a first. So by the matching, we can just solve for a right here. So the one that I just mentioned about, so the quadratic terms, the coefficient of the quadratic term. And this one is the coefficient of the linear term. And then the constant term, we do have negative 1. So solve for a first. So we do have a equals 1/2. Once you solve for a, you can plug in the value of a for the first and the second equations. So we can solve for b and c. So it's a linear system equation, so we got b and c. So b is 1/5, and then c is negative 1/10. And then by plugging the number back to the setup we have for the original expressions for the integrand, we do have 1/2 times 1 over x plus 1/5 times 1 over 2x minus 1, and then 1/10 1 over x plus 2. Because that is just the value of a, the value of b, the value of c. And then we're just integrating the integrand, so we do have 1/2 times natural log of absolute value of x plus 1/10 times natural log of absolute value of 2x minus 1, and then minus 1/10 times natural log of absolute value of x plus 2. That's another typo. Right here, it's supposed to be natural log of absolute value of x plus 2. And then plus constant k. So in integrating the middle term, we have make the u substitution. So we do use that u equals 2x minus 1, which give that du equals 2 dx, and dx equals du over 2. So we can use the alternate method to find the coefficient of a, b, and c in example 2. So equation 4 is the identity. It's true for every value of x. Well, that's just another approach. So solving a, b, and c is pretty much the same thing. Okay, so now let's move on to the next one. So let's say we do have an integrand like this. So dx over the quantity of x squared minus a squared. So you can see that it's the difference of 2 squared for the denominator. So once you're separating the linear factor, we do have a over x minus a, and then plus b over x plus a. And solving that, a and b. So multiply the missing element. So set that equal to 1 to numerator. And then we want to find out the linear term we have. So a plus b got to be 0 because there's no linear term involved for the numerator. And then for the constant term, so let's go back here. For the constant term, we do have capital A times little a, and then capital B times negative little a. So that equals the constant term 1. So we'll look at that right here. So solve for a and b. So we do end up with 1 and 1. 1 and negative 1. And then 1 over 2a, we just want to pull that out because that's the missing element. So take the integral. So we do have natural log of absolute value of x minus a minus natural log of absolute value of x plus a. Again, 1 over 2a, that's just the coefficient. And then it's the indefinite integral, so we need to add the constant c at the end. So here's another formula we can apply for the integral, but don't worry about the formula, so since we don't know what that is. So case 2, q of x is a product of linear factor, and some of which are repeated. Okay, so this one is just like a general description for the cases. So we'll just skip that. So this one shows the pattern, linear factor, and then quadratic factor, and then the higher linear factor, higher power linear factor. So once you see that the linear factor, so let's say we do have something like this. So once you factor the denominator, we can always start it with a over x, and then b over x squared, because that started from linear to quadratic. And then for the x minus 1 to the power of 3, similar. So c over x minus 1, and then d over x minus 2 quantity square, and then e over x minus 1 quantity to the power of 3. And you may notice that you started with the linear factor first. The linear, quadratic, and then cubic. So we just need to raise up the order for the power. So linear first, quadratic, and then the higher power. So now here's another one. So this one you can use the partial fractions by using the long division process, just like what we did previously. And then here's another case, factor by grouping. Or we can do it that way. Again, start with the linear factor. So a over x minus 1. So b over x minus 1 quantity square. And then the different factors. So we do have c over x plus 1. And then multiply the missing element for each rational expression. So we do have this. And then regroup them. So the quadratic terms, the linear term, and then the constant term. So we just want to do the matching. So as you can see that the quadratic terms. So there's nothing for the quadratic term for the numerator. So we can set that a plus c equals 0. And then for the linear term, we can set that b minus 2c equals 4. And then for the constant term, we can set that equal to 0 because there's no constant term for the numerator. So here's what I'm talking about. Quadratic terms, so there's no such thing, so we can set that equal to 0. Coefficient for the linear term, so that equals 4. And the coefficient for the for the constant term, so that's 0. So solve for a, b, and c. So solve for either a, b, or c first. So we got 1 for a, b equals 2, and then c equals negative 1. It's all about the linear system equation here. So that means a is the same as negative c. Okay, so solve for the rest of this. So we do end up with all the value. And then by plugging the number back to the original setup here, the integrand. So we do have x plus 1, using that the long division process. And then the integrals of x squared over 2, integrals of 1, so it's x, and then integrals of 1 over x minus 1, it's natural log of x, absolute value of x minus 1, minus 2 over x minus 1, the integral of this, and then the integrals of 1 over x plus 1, so it's natural log of absolute value of x plus 1, and then plus constant c, or constant k. Combine the like terms, so that's what we got. And then case 3, so case 3 is that q of x contains irreducible quadratic factor, and none of which is repeated. Okay, so we'll take a look at that. Again, this one is just the general description. So let's say we do have something like this. So once you factor it, so we do have the linear factor, the quadratic factor, and then another quadratic factor. So we started with the linear factor, so it's a over x minus 2, so none of those factors are being repeated. And then for the first quadratic factor, we do have x squared plus 1. So the way to rewrite it with the partial fraction, it's bx plus c over x squared plus 1. And then for the second quadratic factor, we do have x squared plus 4. So the way to decompose it is dx plus e over x squared plus 4. So that's just a setup. And one thing that we notice for the formula, so we do have integrals of dx over x squared plus a squared. It's always written as 1 over a, inverse of tangent of x over a plus constant c. So using that, the decomposing structure for the partial fraction, so here's what we got. X to the power of 3 plus 4x, so that equals x times x squared plus 4, factor it first. And then separating the terms out, so we do have decomposing a over x, linear factor. And then for the quadratic factor, we do have bx plus c over x squared plus 4. Again, multiply the missing element compared to the numerator, so we do have a times the quantity of x squared plus 4 plus bx, quantity of bx plus c times x. Regroup them, so for the quadratic factor, we do have the coefficient of a plus b times x squared. And then linear term, we do have cx. Constant term, we do have 4a. Again, we're doing the matching here, so for a plus b, so then that would be 2. And then negative 1, so that would be c. And then constant term, so 4 equals 4a. So we can solve for a and c first. Once we solve for a and c, we can solve for b. Okay, so plugging that back to the original setup for the decomposing, the fraction, the rational expression decomposing, we got 1 over x for the integrand, x minus 1 over x squared plus 4 for the second integrand, and then integrating it. And also we can use the u substitution for the first half of the integrand, and then for the second half, it just considered the inverse of tangent. Okay, so now here's what we found. So using that, the u substitution, we do end up with the, or we can use the formula. So we end up with natural log of absolute value of x plus 1/2 natural log of x squared plus 4 is supposed to be absolute value. And then minus 1/2 times inverse of tangent of x over 2 plus constant k with the partial fraction decomposing. So here's another one. So we can always use the long division first. So we end up with this, the quotient with the remainder. And then for the remainder, we can use the partial fraction decomposing structure. Again, so set that equal to the numerator. And then we want to find out the separations, or we can use that the u substitution technique for this. So let's say that after we factor it, we can use the u substitutions. Okay, so separating the terms out, so we do have x plus 1/8 natural log of absolute value of u plus u squared plus 2 minus 1/4 times 1 over root 2 inverse of tangent of u over root 2 plus constant c. And then u will be considered 2x minus 1 as what we set up previously. And then for that, unplug that and then try to use the binomial expansion. So here's what we got. Okay, so now let's see what else that we have for the partial fraction decomposing structure. So this one is just giving you the structure, how to separate them. So c u over u squared plus a squared. So this one can be written as c times the integrals of u over u squared plus a squared. And then the other part, the constant terms, is just d times the integrals of 1 over u squared plus a squared times du. And now case 4, so that contains the repeating irreducible quadratic factor. Okay, so now let's look at that, the one of the examples. So let's say we do have something like this for the integrand. So we started with the linear and now the linear factor. So then the quadratic factor, and then the quadratic factor with the repeating quadratic factor. So this one is a whole lot more complicated. So we started off with the linear factor. So we got a over x, the non-repeating b over x minus 1. and then cx plus d over the quadratic, and then ex plus f over the quadratic, and then gx plus h over the other quadratic factor with the repeating factors, and then plus ix plus j over the repeating x squared plus 1 to the power of 3, the quadratic factor. So now for the rest of this, we're going to continue with another video for this. So thank you for watching this first half of the 7.4 today. Okay, so I'll see you guys later.